Welcome back to Chemistry Matters and Unit 11, Nuclear Chemistry. In our last video, we investigated radioactive decay. Both you and our students were given the assignment of writing 2 nuclear decay equations. So let's get back out to our classroom so you can see if your equations match those written by our students.
Let's look at the results of the nuclear decay equation problems I gave you earlier. We'll start with Team 1. Please read your work out loud and interpret your results for us.
The first problem had nitrogen-15 going through beta decay. That means 1 neutron changes into a proton and releases a beta particle and gamma radiation too.
Right. Can you explain how your equation represents that reaction?
Sure. Nitrogen-15 is the given reactant undergoing decay. Beta decay means a neutron changed into a proton, so the atom lost 1 neutron and gained 1 proton. The mass number is still 15, but because the number of protons changed, the atomic number changed from 7 to 8. That's why the nitrogen atom changed into oxygen atom.
And we also showed the beta particle, which has a 0 mass number and a special atomic number of -1. We also showed gamma radiation.
Yes, that's correct. Well done, guys. So Team 2, let's look at your work for the next problem.
The problem told us that uranium-235 undergoes alpha decay and then beta decay. So we started by looking at what happens because of alpha decay. Because alpha decay happens first and alpha particles are big.
Right. The periodic table shows us that U-235 has 92 protons because it's uranium. If alpha decay occurs, the atom loses 2 protons and 2 neutrons in the alpha particle. That drops the atomic number to 90 and the mass number to 231.
An atom with 90 protons isn't called uranium, it's thorium, and it's lost 4 particles, 2 protons and 2 neutrons. That means an alpha particle was released.
Sure, but beta decay then causes 1 neutron to turn into a proton, so a proton is gained. That means the atomic number of the daughter nuclide becomes 91. Our periodic table tells us that element number 91 is protactinium, so we use the element symbol Pa.
The thorium decayed into protactinium, 231. We finished the equation by adding the symbols for a beta particle and gamma radiation.
You've all done a nice job balancing your nuclear decay equations. But there are sometimes circumstances in nuclear chemistry that can create unbalanced equations. By 1938, scientists had learned how to bombard uranium atoms with neutrons. Scientists Otto Hahn, Lise Meitner, and Fritz Strassmann found that uranium atoms actually broke apart to produce smaller atoms like barium. They had discovered nuclear fission. They also found that some of their nuclear equations were unbalanced as a result. It turned out that the mass of some of their products was less than the mass of their reactants. But remember from the law of conservation of mass that the total mass of the reactants is supposed to match the total mass of the products. So can anyone think of a reason why their results were unbalanced? Yeah, Caleb.
Maybe some of the particles weren't picked up. They're pretty small.
Yeah, maybe some were so small that they couldn't even be measured. Maybe only the ones with charges could be measured.
Those are excellent questions and interesting hypotheses. What Lise Meitner eventually realized was that some of the mass was being converted into energy. And back in 1905, Albert Einstein had determined how much energy could be released by the conversion of matter into energy. His equations helped these scientists determine how much energy nuclear fission could release. You can learn more about this phenomena in your physics classes. The important thing for this course is to understand that it's possible for atomic fission to produce a total mass that's less than the original mass.
So matter can really be converted into energy?
It sure can. Nuclear fission, as you can see represented here, produces particles moving away from the nucleus at very high speeds. And it can release large amounts of kinetic energy, which is then converted into heat. And we can make use of that energy or radiation. That amount of energy is 200 million times the amount that's typically released from an equivalent amount of coal. So let's explore ways in which radiation is important in our everyday lives. Who can give us an example?
Don't nuclear power plants use the heat from uranium decay to make electricity?
And I believe cancer patients sometimes get treated with high energy radiation, like gamma rays.
Those are both true. Good examples.
Do X-rays act the same way as gamma rays?
That's a great question. X-rays and gamma radiation differ somewhat in wavelength and energy level. Gamma radiation has more energy and a shorter wavelength than X-rays do. But another important difference between X-rays and gamma radiation is that X-rays are emitted from an atom's electron shell, while gamma radiation is released directly from an atom's nucleus during alpha or beta decay.
Don't they also use radioactive materials to see what's going on in our internal organs?
Yes, and many times we call these radioactive isotopes tracers. Small amounts of radionuclides can be injected into a patient's blood. And since these atoms release small amounts of energy, they can be detected outside the body, and they can be used to reveal problems with the blood vessels and organs like the kidney, the liver, or the brain.
When we did the cloud chamber experiment, we learned that smoke alarms use radioactive materials too.
And I think I heard about people using radioactive isotopes to figure out how old fossils are.
You're right. Those are all great examples.
Interesting list, especially that last student who mentioned that we can measure the age of fossils by using radioactive isotopes. But before I can explain exactly how radioactive atoms are used to date fossils, you'll need some additional information. You might remember Ernest Rutherford from our lessons on atomic theory back in Unit 3. In 1890, Ernest Rutherford studied uranium and other radioactive atoms with chemist Frederick Soddy, and they noticed that the isotopes decayed in a predictable pattern. They called this predictable pattern a half-life. Half-life is the time it takes for half of the nuclei in a quantity of radioactive isotopes to undergo nuclear decay. Mathematically speaking, they found that all radioactive materials go through radioactive decay at a rate that changes exponentially. Frederick Soddy found each radioactive isotope has a specific half-life that helps us predict the amount of time needed for half of the atoms in a sample to undergo nuclear decay. Look at this graph of the half-life of the radioactive isotope sodium-24. This graph shows that after about 15 hours, half of the original amount of sodium-24 has decayed and is no longer sodium. This data tells us that the half-life of sodium-24 is 15 hours. Every 15 hours, half of the sodium-24 atoms decay and become a different element. The starting amount produced 400 Geiger counter counts per second, but after 15 hours, only 200 counts per second were recorded. That means that after 15 hours, there were half of the original number of radioactive atoms. Over the next 15 hours, half of that amount had decayed again, from 200 counts to only 100. After about 5 half-lives, the amount of sodium-24 remaining would be almost too small to measure. All half-life graphs have the same shape, but the time scale indicates the rate of decay. For example, some isotopes decay in seconds, while others can take years. So coming back to our fossil example our student raised, you can see how scientists are able to use half-life calculations to determine the age of fossils in ancient rocks. By knowing the rate of decay of the radioactive material in the fossil, they're able to determine how many half-lives have elapsed, which then gives them the age of the fossil. Looking at some examples will help you get a better handle on this concept. So let's go back to our classroom where our students are preparing to calculate the half-life of some radioactive elements.
Let's begin by summarizing what half-life is. Who wants to do that?
I'll try. Half-life is the amount of time needed for half of a radioactive sample to decay.
Exactly. So let's investigate what that definition really means. Each one of you has a box in front of you that contains 100 pennies. Go ahead and open the box and make sure that every penny is face up. That is to say that all 100 pennies should show heads. Okay? Now on the graph paper that I've provided for you, mark the number 100 as the starting amount on the vertical axis. Now close the box, and when I say go, we're going to shake the box for 10 seconds. We're going to say that that 10 seconds represents the half-life for this radioactive element. Ready? Go. Open the boxes and remove any of the pennies that have flipped over and are now tails instead of heads. We'll say that tails means that the atom has undergone radioactive decay. Okay, once you've removed all of the pennies that are now tails, count the number of pennies that are remaining in the box. Record the number of pennies that are still in the box on your graph as the number of atoms that are still radioactive after one half-life. Okay, now we'll close the box again. And same thing as before, when I say go, we'll shake it for 10 seconds, and this will represent another half-life passing. Ready, go. And stop. Now open the box, and again, remove any pennies that are now tails up. Okay, after you removed all the pennies, count the number of pennies that are still remaining in the box and place that number on your graph, and that will correspond to the number of pennies left after 2 half-lives have passed. So continue on with this activity, shaking the box for 10 seconds at a time, and we will do this until we've completed 5 half-lives. I've put both of your graphs up on the monitor. Let's analyze them. Can anyone tell me what you notice when you look at the shapes of the graphs?
Both of the graphs have pretty much the same shapes. There's only a little difference between them.
It seems like the number of pennies was cut roughly in half every half-life. So I guess that's where the name half-life must come from.
Absolutely. Remember, our pennies represent radioactive atoms undergoing a predictable change. Half of the atoms in the sample decay every half-life.
So in this example, do we say that the half-life of these pennies equals to 10 seconds?
Yes, that's the right idea. Half-life is the amount of time needed for half of the nuclei in a given quantity of radioactive isotopes to undergo nuclear decay. And the time needed for that decay will vary depending on the isotope that's being measured. Take a look at this graph. The vertical axis is labeled proportion of radioactive parent atoms that are remaining, and the numbers range from 100% at the top down to 0% at the bottom. Now the horizontal axis is labeled the number of half-lives. This graph doesn't necessarily specify the units of time, that is, whether the half-life is in years or seconds or something else. But what's important to notice is that the half-life always follows a pattern. After one half-life, half of the atoms in the sample have decayed. So how many half-lives would it take to get rid of almost all of the original sample of parent atoms according to our graph? Okay.
It looks like it approaches 0% radioactive atoms at 5 half-lives. But how can we know how long that is?
Great question. And to answer it, we'll need some information about the substance. So let's practice a problem. Radioactive radium-223 undergoes alpha decay to form radon-219 as a decay product. If you start with 120 grams of radioactive radium-223 and it undergoes alpha decay with a half-life of 11 days, how much would you have left after 44 days? Use your whiteboards and be sure to show your work.
All right, so we're starting with 120 grams. In one half-life of 11 days, we'll have half of 120 grams, which is 60 grams. In one more half-life, we'll have half of 60 grams, which is 30 grams. One more half-life, and we'll have 15 grams of radium-223 remaining. So how many days has that been?
Well, 3 half-lives is 33 days for radium-223. We're trying to figure out how much we have left after 44 days, which is 11 more days. So we need one more half-life.
Okay, Splitting 15 grams in half again gives us a total of 7.5 grams, and that's 44 days, which is 4 half-lives.
Okay, let's look at your whiteboards. All right, I see you did a new calculation for each half-life, dividing the number of grams of isotopes in half to represent each half-life. While your drawing helps you get the right answers, using a more structured approach, like a chart, can be very useful, especially when searching for different information.
Why do you already have 0 for the time passed?
That's a great question, and it relates to a common mistake that students can make. If you're running in a race, before the starting gun has fired, how much time has passed?
Well, none.
Right. And half-life calculations are very similar to that. Before you start, no time has passed, so no half-lives have passed. Use a chart like this one to solve the following problem. Radioactive hydrogen-3 undergoes beta decay to form helium-3 as a decay product. If we have 80 grams of hydrogen-3 and it undergoes beta decay with a half-life of 12.3 years, how many years will it take for the sample to degrade to 2.5 grams?
If we start with 80 grams, it'll take 1 half-life, which is 12.3 years, to get to 40 grams. It'll take that 40 grams another 12.3 years to get to 20 grams, which means 24.6 years have passed.
So if we keep completing our chart until we get to 2.5 grams, it looks like it'll take 5 half-lives for 80 grams of hydrogen-3 to decay to 2.5 grams.
But to get the total number of years, we need to multiply 5 half-lives times 12.3 years, the total length of half-life.
So that means it'll take 80 grams of hydrogen-3, 61.5 years to decay to 2.5 grams.
Excellent. What you've just done is exactly what scientists do when they determine the age of fossils and rocks, like the ones that you see here on the lab bench. Once they know the rate of decay of the radioactive isotope that's found in the fossil, they simply measure the mass of the remaining isotope and then the mass of the decay product atoms. If half of the radioactive isotopes remain in the fossil and have not yet decayed, we know that the fossil is 1 half-life old. An alternative, more quantitative approach to solving half-life problems is to use an equation like this. You'll notice that this equation has an exponent in it. And in case you haven't covered algebra yet, the inverse operation for exponentiation is the logarithm. This can be accomplished on most calculators by first calculating the desired value and then pressing the log button to get the logarithm of that value. So if you ever have a problem in which you must solve for the number of half-lives that have passed, the easiest way to do that is to first divide both sides of the equation by the initial mass. To do that, we'll multiply each side by 1 over the initial mass. And you'll get this, which is the mass final over the mass initial equals 0.5 to the nth power. Then we'll take the log of both sides of this equation so that you get the log of final mass over initial mass equals n times the log of 0.5. And then in our previous example, we would substitute 2.25 in for our final mass and 80 grams in for our initial mass. And on the left-hand side, you'll see that 2.5 divided by 80 equals 0.0281. So you take the logarithm of that, and you'll get negative 1.5 is equal to n times the log of 0.5, which is negative 0.3. To solve for n, you'll divide both sides of the equation by negative 0.3, again by multiplying each side by 1 over negative 0.3, and you would get 5. This means that 5 half-lives have passed. And 5 times 12.3, which was our half-life for this problem, equals 61.5 years. Lastly, you can calculate the half-life of any radionuclide if you have some additional information. For example, let's say we have 200 grams of radioactive thallium-207 that undergoes beta decay to form lead-207 at an unknown rate. If there are only 12.5 grams of thallium-207 remaining after 20 minutes, what is the half-life of thallium-207? Try working this out with your partner on your whiteboards.
Let's see. We know we're starting out with 200 grams of our sample.
We can trace the half-life process, but we don't know the times yet, so let's leave that part blank.
So, starting with 200 grams, after one half-life, the mass will be down to 100 grams. Then 50. Then 25. And then down to the mass we were given, 12.5.
Great. Now we know it takes 4 half-lives to get to 12.5 grams. So we now need 4 equal increments to get to 20 minutes.
So let's just divide 20 minutes by 4 half-lives to get 5. So a half-life of thallium-207 is 5 minutes.
Well done. And if you want to solve this problem using the equation that we did before, you would again first divide both sides of the equation by the initial mass, which we can accomplish by multiplying both sides of the equation by 1 over the initial mass. And that will give us this expression. Final mass over initial mass equals 0.5 raised to n. Next, we could take the log of both sides of the equation so that we could bring the n down. So we would get the log of the final mass over initial is equal to n times the log of 0.5. And again, substituting the values in from our problem, we knew that the final mass was 12.5, our initial mass was 200. And so if we divide 12.5 by 200, we get 0.0625. So now we can take the log of 0.0625, which is negative 1.2, and set that equal to n times the log of 0.5. Now if we take the log of 0.5, we get negative 0.3. We want to get n by itself, so we'll divide both sides of the equation by negative 0.3, which again is the same thing as saying multiply each side of the equation by 1 over negative 0.3, and that will get us n by itself, which we find to be 4. So that will tell us that 4 half-lives have passed. And we know that 20 minutes has elapsed, so we divide that 20 minutes by 4 half-lives, and we find that each half-life must have been 5 minutes.
Calculating half-lives is an important part of nuclear chemistry, and it can give scientists a lot of information. You can find more practice with half-life calculations in our Chemistry Matters Toolkit. When you feel comfortable doing those, you'll be ready to move on to the next video on the Unit 11 playlist.